All right, let's talk about one of the most useful rules of thumb in all of statistics. Seriously, it's called the 68 95 99.7 rule, or the empirical rule, and it's a real game changer.
So picture this. You're looking at a huge pile of data. It could be anything. Test scores, heights, you name it. How in the world do you make sense of it all? How do you figure out what's normal and what's, well, a little weird without getting completely bogged down?
So let's jump right in. To answer that question, we first have to get a feel for the landscape where all this data lives.
You know, what's so amazing is that if you plot out a ton of real-world data, this one particular shape just keeps showing up again and again. You probably know it as the bell curve, but its official name is the normal distribution. It's almost like it's nature's favorite pattern. Okay, so we've got this bell curve. Now what? How do we actually use it? Well, that's where our main tool for today comes in, the empirical rule. It's just the fancier name for that 68 95 99.7 rule we mentioned. Seriously, think of this rule as your secret weapon. It's a mental shortcut that lets you quickly understand how data tends to bunch up around the average, or the mean, as long as you're looking at a normal distribution. Now, to really get this, we only need to understand two things, and this drawing lays it out perfectly. First, you've got the mean. That's the Greek letter mu right in the middle. It's just the average of all your data. And second, you have the standard deviation, or sigma. Just think of sigma as one standard step away from the average. It tells you how spread out everything is. Okay, so the first piece of the puzzle, that first number in our rule, is 68%. This is the real heart of the data.
So what does that actually mean? It means that for any data that follows a bell curve, about 68% of it, so roughly 2/3, is going to be within one step, or one standard deviation, of the average. Let's make that real. Say you have a bunch of CDs and the average playtime is 35 minutes. If the standard deviation is 5 minutes, our rule tells us that about 68% of those CDs will last somewhere between 30 and 40 minutes. Simple as that.
All right, now let's take one more step out from the center. The next number in our rule, 95%, captures almost everything you'd consider typical.
This is what you find if you go out 2 standard deviations from the mean. It's often the benchmark for what we consider normal. So, back to our CDs, a whopping 95% of them will have a playing time somewhere between 25 and 45 minutes.
And finally, we get to 99.7%. If you go out 3 standard deviations, 3 of those steps from the average, you've basically captured everything. A data point that falls outside of this range is exceptionally rare. We're talking about something that happens only about 3 times in 1,000.
But, and I can't stress this enough, this is a huge but, we have to talk about the fine print. This is absolutely the most important part of this whole explainer because this is where people get into trouble.
And you don't have to take my word for it. This is a direct quote from a guide on common errors from the AP statistics exam. It says it all. The absolute key is this. If your data doesn't look like a bell curve, this rule is useless. You just can't use it.
And this slide shows you exactly why. The rule works for a normal distribution because it has what are called thin tails. That just means those crazy, way out there events are incredibly rare. But a lot of systems in the real world, especially in finance, have fat tails. In those cases, the chances are more spread out, and those wild, extreme events happen way more often than our nice, tidy rule would ever lead you to believe.
And if you want a really dramatic, real-world example of this gone wrong, look no further than the Black Monday stock market crash in 1987. It was so extreme that if you incorrectly assumed the market followed a bell curve, you'd calculate it as a 36 sigma event. 36! Remember, our rule says pretty much everything is within 3 sigma. 36 sigma is so far out there, it should be basically impossible. That's all the proof you need that the market is a fat-tailed animal, and trying to apply this rule to it would be a disaster.
Okay, so now that we know the rule and its big, scary limitation, let's flip things around and see how it's used correctly, because it's incredibly powerful when you know what you're doing.
This is where we get the famous 3 sigma rule of thumb. It's basically a super fast way to spot something weird, because anything that falls outside of that 3 sigma range is so rare, it gets a flag. In a factory, for example, if a product measurement is outside 3 sigma, it gets pulled for inspection. It's an outlier, and it needs a closer look.
And what's so cool is seeing how different fields have their own standards for what counts. In social sciences, hitting 2 sigma, that 95% mark, is often enough to be called statistically significant. In quality control, as we said, 3 sigma flags an outlier. But then you get to particle physics. To claim you've discovered a new particle, like the Higgs boson, you need to hit 5 sigma. That's a 1 in 1.7 million chance of being a fluke. The bar for rewriting physics textbooks is understandably really, really high.
All right, for our last section, let's get a little nerdy for a second and peek under the hood of the math itself. Let's ask a really basic question about how this whole thing is built.
I mean, have you ever stopped to wonder why the formula for standard deviation has you square the differences from the average? It seems kind of complicated, right? Why not just use the absolute value? I mean, that feels way more straightforward.
It's such a great question, and the answer actually tells you a lot about why statisticians do what they do. First off, squaring gives a lot more weight to the big differences. It really punishes outliers. Plus, from a pure math perspective, it's just nicer. It gives you a smooth curve that's easy to work with in calculus. It also connects to geometry. It's basically the same idea as the distance formula you learned in school. And critically, it lets you do some really neat tricks later on, like adding variances together.
And that really brings us to the big takeaway here. The statistical tools we use, even a seemingly small choice like squaring a number, they aren't just abstract formulas in a textbook. They are powerful lenses. They literally shape how we see our data, how we define what's normal, and in the end, how we understand the world around us.